Hello, everyone. This is Peng Zhao from the University of Tennessee, and welcome to today's Combustion webinar. And it's my great pleasure to introduce our speaker, Dr. Alison Ferris. Dr. Alison Ferris is currently a visiting research scientist at TU Darmstadt in the Institute of Reactive Flows and Diagnostics, as well as a postdoc scholar at Princeton. Prior to her current appointments, she was a research scientist at Stanford, where she oversaw multiple research initiatives in Professor Ron Hansen's shock tube and optical diagnostic lab. Her research interests include using shock waves and optical diagnostics to study the design, chemical synthesis, and reaction kinetics of sustainable fuels for use in current and next generation energy and propulsion systems. Dr. Alison Ferris received her PhD in mechanical engineering from Stanford in 2021, focusing on the development of a high temperature laminar flame speed measurement technique and a combined gas chromatography laser absorption diagnostics for comprehensive time-resolved species measurements behind reflected shocks. Dr. Alison Ferris received her master in mechanical engineering from the University of Wisconsin-Madison Engine Research Center in 2014. She will start as assistant professor at Princeton in 2024. Well, let's welcome our speaker, Dr. Ferris. The podium is yours.
Thank you very much, Peng. Thank you for the kind introduction. And thank you all for tuning in today. Yeah, I'm excited to share with you my talk on the development of the shock tube laminar flame method and its application to the study of alternative fuels. As Peng mentioned, I currently hold a dual appointment at both TU Darmstadt and Princeton, but the work I'll be talking about today comes from my time as both a PhD student and a research scientist in the Hansen Research Group at Stanford University. All right, let's dive in. So I guess first you might ask, why develop a shock tube-based method for studying laminar flames? Well, I guess that the main underlying motivation here is that we wanted to be able to measure and study flames and measure laminar flame speeds at previously unexplored high temperature conditions. And so that then begs the question, well, why do we even want to study flames at high temperatures? And so, well, engine operability, efficiency, and emissions, they're all governed by high temperature flame dynamics. In particular, the laminar flame speed is a global property that captures thermodynamic, transport, and chemical kinetic information about a fuel and air mixture. Laminar flame speed is defined as the rate at which a planar laminar flame, 1D, propagates through a quiescent mixture of unburned fuel and air, or fuel and oxidizer mixture. And throughout the talk, I'll be abbreviating it as this variable here, SU0. So on the right, what I'm showing here is a plot of pressure versus temperature and the pressure and temperature conditions that you would expect to see in, for example, an IC engine, both under conventional operation as well as some more modern combustion approaches. So something that's interesting to note, actually, is that the vast majority of laminar flame speed data available in the literature falls in this small yellow box right here, right? Low temperature, relatively low pressure. There have been multiple techniques that have been developed in order to allow us to measure flame speeds at higher temperatures and pressures. So among those, for example, we have flow-based flame techniques that allow us to probe laminar flame speeds at low to moderate temperatures and pressures. We have the constant pressure spherically expanding flame technique, which allows us to measure flame speeds up to and exceeding about 60 atmospheres of pressure. And then we have the constant volume spherically expanding flame technique, which allows us to measure flame speeds along compression isotropes. Something you'll notice, however, is that all of these techniques seem to be limited to temperatures below, say, roughly 750 Kelvin. But we know that engines operate at temperatures and pressures higher than that, right? So one of the things that limits these techniques is what we can call, say, the spontaneous fuel reactivity limit. And so what I'm showing now in this plot on the right, these are now contour lines showing ignition delay times for stoichiometric and heptane in air. And what you'll notice is that, say, the ignition delay time of N-heptane at, say, about 700 Kelvin and 20 atmospheres is about 10 milliseconds. Now, a lot of these approaches that are used for measuring laminar flames, they typically heat the fuel and air mixture using conduction or even combustion to get to those high unburned gas temperatures. What that means is that these heating processes actually take seconds, if not minutes, to get the fuel up to the temperature and pressure that we're interested in studying it at. Now, if you have a fuel that's starting to react on the order of milliseconds, but it takes minutes to heat this up, you can see where you start to have an issue here, where all of a sudden your fuel is going to start reacting before you're even able to run your laminar flame speed experiment. And so that's one of the main reasons why these approaches are limited to lower temperatures. What that means is that there's a need for high temperature flame speed data in order to inform the design of these next generation high efficiency engines. And so the solution that we came up with and that we've been working on for the past couple of years is what we call the shock tube laminar flame method. So that's the main focus of my talk today. I'll talk about the development of this shock tube laminar flame method. So first I'll start with some shock tube fundamentals for those who aren't very familiar with shock tubes. I'll then talk a little bit about the first generation laminar flame method. So this actually encompassed most of my PhD work, is that first generation method. And then I'll move on to how we designed a new sidewall imaging flame test section, which then led to what we call now our second generation laminar flame method. After that, I'll then, for the second half of the talk, switch to how we actually now apply this method, specifically to the study of two different case studies. So one looking at ethanol and isooctane laminar flame speeds, and then give you a sneak preview of some of our most recent ammonia flame speed work. All right, so let's start off with some shock tube fundamentals. So what is a shock tube? A shock tube is an experimental facility that we use to study high temperature chemistry in a controlled environment. I'm showing a picture of it here. So in a nutshell, it's a very long stainless steel tube, but it acts as an impulse heater. So what we use these tubes for is we use them to generate shock waves, which then shock heat fuel and air mixtures, for example, up to elevated temperatures and pressures. And we're able to shock heat these fuels to those high temperatures nearly instantaneously. So this facility that I'm showing here, this is what we call our flexible application shock tube at Stanford University in the Hansen group. So how do these tubes actually work? Well, you have a long tube, as I mentioned, and it's divided into two sections. You have a driver section and you have a driven section, and they're separated by a diaphragm, which is typically a piece of plastic or thin metal. So in a typical experiment, you'll first fill your driven section with the fuel or oxidizer mixture that you're interested in studying. That's usually filled to pretty low pressure. And then you'll fill the driver section with high pressure gas, typically helium, nitrogen, or a combination of the two. So in this experiment, you've now got your driven section filled. You'll start to fill your driver section, keep filling with high pressure gas until ultimately the diaphragm bursts and it sends a shock wave down the tube. That shock wave then hits the end wall and reflects back. And it's in this post-reflected shock region of gas that we then do our experiments. So some of the key characteristics of a shock tube that are useful for example, studying laminar flames, we can use them to generate tunable temperature and pressure conditions. So we can hit a wide range of temperature and pressures, ranging from about 450 Kelvin up to 12,000 Kelvin or even higher, and also pressures ranging from subatmospheric to hundreds of atmospheres. Also, a shock tube is what we consider nominally a 0D reactor. So because this gas behind the reflected shock stagnates, you now have gas that is just sitting there at the designated temperature and pressure, and we can now model it as a 0D reactor. And finally, shock tubes have a very well-defined time zero. And so what I mean by that is because we're using a shock wave to shock heat these mixtures, we know very precisely when those mixtures have reached the temperature and pressure that we're interested in studying, because that shock process happens over a matter of microseconds. So that means that we have a very well-defined time zero. So maybe you can now see how these various characteristics of a shock tube might lend themselves nicely to studying flames at high temperatures. All of a sudden, now we have a nearly instantaneous method for heating these fuel and air mixtures up to high temperatures, which allows us to overcome the spontaneous reactivity limit that's seen by these other conventional approaches. And so in the end, we're able to now develop this shock tube laminar flame method that allows us to measure laminar flame speeds at the highest possible unburned gas temperatures, right? And so what I'm showing now on the figure on the right are the temperature and pressure regimes that we can actually access using shock tube. All right, so with that general background, let's first talk a little bit about the first generation shock tube laminar flame method. So this is what I developed as part of my own PhD work. And so just to give you an overview, here's a little cartoon of what the shock tube looks like. Pretty standard shock tube. The only sort of bell and whistle on this one is that we now have an optically accessible end wall at the end here, which allows us to see into the shock tube. So the main goal of this first generation method was to measure high temperature flame speeds in a shock tube. Pretty simple, not as easy in practice to implement, but the strategy that we went with was initiating laminar flames behind reflected shock waves using laser-induced spark ignition, and then subsequently we want to then observe the propagation of this flame. Something to note, a lot of the conventional flame speed approaches, measurement approaches, they use electrodes in order to spark ignite the flames. But unfortunately, we're not really able to put electrodes into a shock tube, right? We've got shock waves going down this tube and reflecting. And so we had to use a sort of a non-intrusive method for actually spark igniting these flames. So that's why we've now adopted the laser-induced spark ignition approach. All right, so if we look a little bit closer at this setup, this is just a zoom in essentially on the end section of the shock tube. And so for these experiments, we had a high-speed camera and a UV intensifier, and a bandpass filter that allowed us to capture OH star chemiluminescence through the end wall. And you can see here as well this a neodymium YAG laser that we used and focused down to a point in the center of the shock tube, which allowed us to spark ignite these fuel and air mixtures. So a typical experiment looks something like this. You have the incident shock, reflects off the end wall, and then the laser is triggered and generates a spark and then a flame propagating in the shock tube. So here's a look at what some of these initial images looked like. So again, this is through the end wall, and this is just chemiluminescence. So OH star emission, so emission from excited OH radicals. And so in this experiment that I'm showing, this is ethane in air with a phi of 1, and this is a shock heated experiment, shock heated up to 488 Kelvin and 1 atmosphere. So I'll go ahead and play the video here. We first see the spark, and then we see this flame as it propagates. So for each experiment, we get a set of images like that, and then we want to process them in order to pull out a laminar flame speed, right? And so just very briefly, I'll go through what the approach that we took in this first generation method. But so essentially we looked at each image, we binarized it, we used a gradient-based edge detection approach, and then we're able to determine a centroid of each flame image. And then from that, we were able to basically locally track the radius of the flame at various radial angles around the flame. And so from that, we were able to, by tracking that in time, we were able to get a burn gas flame speed, this SB variable here. And we were also able to calculate local stretch rate. So basically, it's a function of surface area of the flame. So by getting those two parameters from the sequence of images, we were able to generate a plot like you see on the right here. So we have burn gas flame speed versus stretch rate. And all these data points is basic. Each data point is basically an individual flame image. And so for each experiment, we want to be able to identify this quasi-steady state or this quasi-steady growth region in the flame. So we want to make sure that we're not considering data that's impacted by ignition or it's impacted by late time flame instabilities. And so once we identify this quasi-steady region, we then use a linear curvature model in order to determine this SB naught parameters. This is now the burn gas flame speed, or the flame speed relative to the burn gas unstretched. And then from that, and knowing using continuity, we then are able to determine SU naught, or the laminar flame speed. So here's a look at some of this early data. So this is from our first publication that I wrote in 2019, so now 4 years ago, where we focused on high temperature methane and propane flame speeds. And so moving from left to right, the black dots here are our experimental measurements. All the other points are either literature results, and the lines are model predictions. And so you see methane here. In the middle, we have our propane and air measurements. And then on the right, we've got propane in a sort of modified air oxidizer. So we've replaced here about 32% of the nitrogen with helium. So at the time, these are actually the highest temperature propane laminar flame speed measurements ever published. And that was exciting, but we obviously saw that there was some room for improvement, right? So for example, we wanted to be able to reduce the scatter in our measurements. We also wanted to be able to reduce the uncertainty associated with each point. And we also wanted to be able to push to higher temperatures. So interestingly enough, you'll notice that our methane flame speeds and our propane flame speeds, these are measured in air, worth noting. We weren't reporting any data above about 580 Kelvin. And so the reason for that is because at higher temperatures, as we went above that roughly 580 Kelvin point, we started to see flame distortion. And so we actually didn't report any of those distorted flames in the initial work. We just wanted to focus on nice laminar flames that were propagating appropriately. But we are limited in temperature space by this flame distortion. So here's what I mean by distortion here. So this is a look at a methane air flame experiment, shock heated to 592 Kelvin. And from left to right, we're going in time. And so we see, okay, initial flame kernel, and then we start to see this sort of this haloing effect, right? And so what was interesting to note is that this is actually temperature dependent as well. So if we look at a methane air flame at 558 Kelvin, for example, it actually looks fine. We have a nice stable flame. But even just increasing the temperature by, say, 25 Kelvin roughly, you end up with this haloing effect. And as you keep going up in temperature, you actually see that that little halo in the middle starts getting smaller until we reach a point where the flame is just completely distorted for the whole experiment. Now, these aren't your typical thermodiffusive or hydrodynamic instabilities, right? So what we wanted to understand was really what causes this flame distortion at higher temperatures. And so in order to get to the bottom of this, we performed what we call a meta-analysis of factors affecting flame stability in a shock tube. And so basically what we did is, at this point, we say, okay, we've taken a lot of measurements of different fuels and different conditions. Let's take a look at all the data and just take a step back and try to understand, where do we start to see this instability happen, or when do we start to see flame distortion? And is there some factor, can we try to figure out what kind of experimental parameter is actually causing or linked to this sort of critical temperature beyond which we see flame distortion? And so what I'm showing on the right here, this is actually a visual summary of all the experiments that we considered. So on the left axis, you see basically the fuel and the oxidizer mixture that was considered in that set of experiments. You also see notes on what pressure that experiment was at, and also whether it used air or, say, argon, and also where the spark ignition event occurred relative to the end wall. So some of the experimental parameters that we considered in this analysis included the pressure, so the pressure of the experiment, gamma, so the ratio of specific heats of the test gas, the average molecular weight of the test gas, the Lewis number of the test gas, and then also the spark location, so where we are actually sparking those flames within the shock tube. So we performed then a logistic regression analysis in order to determine an expression that would allow us to basically predict this T critical, or the temperature at which our flames transition from stable to distorted. And we came up with the following expression down here. I won't go into the math too much, other than to say that by using this expression and fitting it to the data, we were able to predict 93% of the time, we were able to appropriately or accurately predict this critical temperature, which we saw transition from stable to distorted flames. And so using these coefficients down here, these theta values. So some of the major takeaways here, if we actually look at these theta values, these exponential values, what we find is that these exponent values, the largest one has to do with gamma of the test gas, so the ratio of specific heats. And so what we find is that gamma is the largest value. It has the strongest impact on this critical temperature where we go from stable to distorted flames. And not only that, but we found that argon is a superior diluent to nitrogen. And so you can actually kind of just see that from the data that I'm showing in this figure here. Just if you take a step back, the two data sets that have the highest critical temperature, right? So where we're able to obtain stable flames at the highest temperature, it's these two blue data sets right here, right? The dark blue and the light blue. And something that they have in common is that they're both conducted with argon as the diluent in these experiments. The rest of them are either in air or helium. Something else to note is that the next largest factor here is the spark location. And so that, again, we can see from this figure, if we now look at the difference between this dark blue data set and this light blue data set, they're exactly the same, except for the fact that the light blue data set was taken by spark igniting the flames 2 centimeters from the shock tube end wall. So from this, we've learned that the test gas mixture that we're using and that we're in which we're spark igniting these flames, that's important. And where we're spark igniting these flames in the shock tube, that's also important. Okay, but we wanted to be able to look into this a little bit more and be able to figure out how can we optimize, for example, where we spark ignite these flames. We are limited in our test facility because, as you saw in the first generation approach, we were basically spark igniting these flames through a small optical port. So we wanted to have better flexibility in our ability to run these experiments. So that led to the design of what we call the sidewall imaging flame test section, or affectionately known as SWIFT. Every new test section needs a cool name. And so the primary goals of the development of this test section were to, one, expand our sidewall imaging access while still minimizing flow disturbances. So we didn't want to, for example, put in flat square windows in a round facility. We wanted to minimize our flow disturbances through this test section. We wanted to enable sidewall schlieren imaging, so go beyond our emission imaging that we had in the first generation. And we also wanted enhanced experimental flexibility, right? So the ability to actually move about where we're sparking the flame within the shock tube. I should also note that this test section was designed by one of our PhD students, Adam Sousa, and you can read much more about it than the details that I'll present here in his PhD dissertation. Okay, so the first design iteration actually that Adam went through was to just use singlet lens windows. So what that means is just using curved windows on this test section, one on each side, allowing us to see through the facility. In order to assess how this might work, Adam did a ray tracing exercise, which you can see here in the bottom right. So basically, this is looking at if you have a ray of light coming in from the left and it goes through both lenses, where does that ray come out relative to where it went in? And so that's what's being now plotted here on the far right, is what we call this aberration, right? And so what we see is if you look through the center line of this facility and these lenses, you see very minimal distortion, right? Everything looks fine. But now if you look a little bit higher or a little bit lower from that center line, you start to see pretty significant distortion. And honestly, anyone who's tried to look through a round facility using round windows, you're very familiar with this, right? It just looks like a lens when you're looking through it. Okay, so that would not be an ideal scenario, or we have to do a lot of corrections in order to do something like schlieren imaging through this test section. And so the second iteration that Adam considered was now using sidewall cemented doublet windows. So instead of just using one window, actually cement two together. And so what we see now, if we again go through this ray tracing exercise, looking at the rays coming in and coming out, it looks a little funky, but something that you should note is the value here on this axis. If we go back to the singlet lens, we see that we are going from -20 to 20 arc minutes, right? But now by using the cemented doublet lenses, we now have aberration going from -0.5 to +0.5. So we've improved upon the aberration by a factor of 40, right? And that's huge. And so what we find is that this is actually sufficient in order to do schlieren through this test section. And so really these cemented doublet windows are really a first of their kind for imaging through round facilities. So here's what this looks like in SolidWorks land. So we have a 3D rendering on the left, looking at it from the side, this test section, and then here's a look at the end view. And so we have these large cemented doublet side wall windows. So they're 18 centimeters wide by 6.4 centimeters high. We also have these high aspect ratio slot windows. So those are 18 centimeters long, 2 centimeters wide. And then we have, we've maintained basically the optical end wall, which has a diameter of 8 centimeters. Here's what this looks like in real life. So you see a photo of the test section on the left. And on the right, here's a look at that cemented doublet. So the two lenses. So the inner one that actually interfaces with the gas in the shock tube is made of fused silica. And the outer one is BK7 optical glass. So really, for these kinds of flame experiments that we're trying to conduct, this test section has really been transformational in allowing us to study the flames in the way that we would like. And so this test section now led to the advent of what we call our second generation shock tube laminar flame method. So I'll go through that briefly now. So some of the primary improvements over the first generation method incorporated into the second generation shock tube laminar flame method include using argon as a primary diluent instead of nitrogen or air. We now have simultaneous end wall and sidewall imaging capabilities. And we also now can flexibly choose where we actually spark ignite these flames within the shock tube. In terms of instrumentation, we have now high-speed imaging that we're conducting through the sidewall. So this is looking at schlieren imaging, so density gradients through the sidewall. And one of the key factors here is that this whole system is actually on a rail, so we can move it left and right in order to be able to flexibly, again, spark ignite these flames in various locations. Simultaneously, we have end wall imaging, and so this is UV-intensified chemiluminescence. So in most of the experiments that I'm presenting today, we are looking at excited CH radicals. And then in addition to that, we're maintaining that laser-induced spark ignition system. And so we're, again, using a neodymium YAG laser. This time it's actually coming from the top of the shock tube, the direction of the laser, and then allows us to spark ignite the flames. So in a typical experiment, here's what this looks like. Again, incident shock comes, reflects off the end wall. We then trigger the laser to then spark ignite these flames, which then ultimately propagate. Let's take a look at some of the images that we get from this second generation method. So this experiment that I'm showing here is looking at propane flame speeds. This is propane in what we call argon. Very clever. So basically it's air, but we replaced that 79% nitrogen with 79% argon. So that's what we call argon. So this is propane in argon with the equivalence ratio of 1. And this experiment has been shock heated to 650 Kelvin in 1 atmosphere. And we're actually spark igniting this one about 8.5 centimeters from the end wall. So what I'll show here is simultaneous sidewall schlieren images, as well as emission images from the end wall of the shock tube. So here we go. First, you'll see the incident shock. Now it hits the end wall out of frame and comes back. So that's now the reflected shock. And then we have the spark event and then flame propagation. So again, these videos are roughly synced up from the sidewall and the end wall. All right, so once we have those images in hand, we actually also adopted a new approach for our data interpretation. And so we're now using what we call our area averaged linear curvature model. And so essentially what we're doing is we're extracting flame front contours from these schlieren images. And so something that we saw when comparing end wall images with sidewall images is that we see that the flames are basically symmetric about the axis of the shock tube. So that means that these flames are cylindrically symmetric about the axis of the shock tube. So when we're looking at them from the side through the shock tube, the axis of the shock tube, for example, in this image, is running from left to right. So what we're calling this z-axis here. So what we can do from these images is we can define essentially a vertical extent of the flame at each as we march in space across the z-axis. And then from that, we can get an effective radius at each z-axis position. And so this effective radius is therefore what we can then use to calculate things like our average flame speed. So this is our average propagation rate relative to the burn gas. And so that's defined here as the time rate of change of the volume of the flame over the surface area of the flame. And we can also define then average flame curvature, which is essentially related to the surface area of the flame. Again, all calculated relative to this effective radius as a function of z through the flame. So by taking this approach and by using this area averaged model, we find it does not rely on the flame being stationary. So even if there's some slight movement of the flame within the shock tube, it doesn't matter because what we're essentially looking at is a volume over an area. And also it does not impose any sort of spherical assumption on the flame, right? So that means that we can account for some distortion, such as what I'm showing in this image up above. So once we have the average propagation rate as well as the flame curvature, we then want to extrapolate these to zero stretch in order to determine the laminar flame speed. So we're once again using a linear curvature model. If we plot our data on the right, you see, again, this is the burn gas flame speed versus curvature. And what we're pulling out are what I'm showing here, these filled dots are basically what we then fit in order to extrapolate to zero stretch using this linear curvature model. And so finally, once we have then this unstretched flame speed relative to the burn gas, we can then rely on continuity once again to determine the laminar flame speed. Okay, so I've now talked you through sort of the evolution of the shock tube laminar flame method. And so what I'd like to do next is now focus on 2 case studies. So let's take a look at how we've applied this method to the study of ethanol and isooctane flames. After that, I'll then talk about some ammonia flame work. All right, so we use the 2nd generation shock tube laminar flame method in order to study high temperature laminar flame speeds of ethanol, isooctane, and then blends of the two. So specifically looking at E50 and E85, where E50, for example, is a 50-50 by volume blend of ethanol and isooctane. We looked at flame speeds ranging from unburned gas temperatures of 450 to 1020 Kelvin in 1 atmosphere. And we also investigated a range of equivalence ratios from lean to rich. So I'll now show two videos representative of some of these experiments. So on the left, I'll first show an ethanol experiment, and then on the right, I'll show an isooctane experiment. So in this ethanol experiment, this is ethanol, stoichiometric ethanol in, again, argon. So again, we've replaced that 79% nitrogen in air with argon. And this experiment had the gas shock heated to 499 Kelvin and a pressure of 1 atmosphere. So I'll go ahead and play the video. Again, incident shock, reflected shock, and then we see spark ignition and flame propagation. All right, that's the ethanol case. And on the right, I'll now show an isooctane example. And so this is isooctane and argon, shock heated to 854 Kelvin in 1 atmosphere. Incident shock, reflected shock, spark ignition, and flame propagation. All right, and so once we have those flame images and we go through our linear or area average linear curvature method approach for analysis, we end up with flame speeds that look like this, right? And so each column here is a different fuel, and each row is a different equivalence ratio. And what we're showing, the gray points are experimental results, whereas the lines are kinetic model predictions. I know it's a lot, so instead, let's just focus on one fuel. So let's take a look at, for example, these ethanol flame speed measurements. So again, this is ethanol and argon at 3 different equivalence ratios over a range of temperatures, all at 1 atmosphere. So one key observation here, if you just look at these 3 plots, is that the kinetic models seem to systematically overpredict the high temperature ethanol laminar flame speeds. And so of course, we're experimentalists, so we want to understand why. Why are these kinetic models overpredicting the measurements? So in order to do that, we performed a sensitivity analysis. So looking at sensitivity of ethanol laminar flame speeds to the various reaction rates in the models. And so again, this is looking at 6 different kinetic models. What we find is that all 6 of the models essentially agree that these 3 reactions that I've highlighted here are essentially the most important or the most significant ones impacting ethanol laminar flame speed when we run these simulations. And so these 3 reactions are, first, H plus O2 goes to OH plus O. Usual suspect, comes up a lot in reaction chemistry or combustion chemistry, simply due to the fact that it's a chain branch reaction. So that's not a surprise. And then next we have CO plus OH goes to CO2 plus H. And then third, we have third body collision reaction of HCO plus M goes to CO plus H plus M. So we're interested in trying to understand, are these 3 reaction rates within each of the models, are these 3 reaction rates responsible for that discrepancy that we see between the model predictions and the measurements? And so in order to do that, we looked a little bit deeper into what the reaction rates were that these models were actually employing. And so this plot here on the left, what I'm showing, the lines indicate the reaction rates used by the models, the various models, and the data points are actually measurements of these various reaction rates that exist in the literature. And so first, starting with this first reaction of H plus O2 goes to OH plus O. It's a very well studied reaction rate. We actually have data across this whole temperature range that we're looking at here, for example. And what we find is that the reaction rates used by the models differ by up to about 62%. It is worth noting, however, that you only see 3 lines here because 4 of the 6 models actually do use the same reaction rate. And so they're all under this teal line here, this teal line being NUIG 1.3. So in the end, we do see, however, that this reaction rate used by NUIG 1.3 and these other 3 models, that reaction rate does show the closest agreement with available experimental results. Reaction 2, the CO plus OH goes to CO2 plus H reaction. We see that the reaction rates used by the models differ by up to about 41%. What we see is that the reaction rate R2 used by the Lawrence Livermore and the NUIG models, this R2 rate that they're using shows the closest agreement with these available experimental results. And then third, this R3 reaction, so HCO plus M goes to CO plus H plus M. We see that the reaction rates used by the different models differ by up to about 218%. And we also see that they have different collision efficiencies for various molecules. What we do see is that the reaction rate for this reaction, the reaction rate used by the Ramsey group, we see that this actually shows the closest agreement with the available experimental results for this reaction rate. So next, what we want to do is try to modify these kinetic models in order to have common R1 to R3 expressions, right? We want to see if we bring these rate expressions into convergence for these different models, does that take care of our problem? And so in order to do that, we had to choose which R1, R2, and R3 rates would be most appropriate. And so for that, we just went with looking at the reaction rates that actually most closely match the experimental results that are out there for these reaction rates. And so that means that we used the R1 from NUIG 1.3, R2 from the Lawrence Livermore model, and then R3, that reaction rate, the one that was used by the Ramsey group. So here's what this looks like. So now if we redo our kinetic simulations with the modified models and now compare that to our experimental results, we see the following. The modified models are in the dashed lines here. Actually doesn't help much to just look at this. It helps to look at the original. So here, let's toggle back and forth a couple of times. But so this is what the models originally predicted. And now here's what the models predict after we've made the modifications to R1 to R3, right? And so we see a few things. First, we see that by just changing these three reaction rates or bringing them basically into agreement with existing experimental data for these rates, we see that we're basically able to bring these model predictions into agreement with the experimental results within the experimental uncertainty of these measurements. Not only that, but we also see better agreement between the kinetic models themselves, right? So previously with the original models, we saw there was an average difference of about 10% in their predictions, and now we see that they're actually showing an average difference of about 6%. So this is just sort of an interesting case study, but what it shows is that basically by using rate constants that align with high accuracy experimental measurements, it really leads to superior kinetic model performance. And that's an important takeaway here. Okay, so switching gears slightly, something that we often hear, okay, you're now measuring flame speeds in argon, but most fuels are oxidized in air, not argon. It's always reviewer number 2. And so something we want to look into is, okay, if we're taking our measurements in argon or in an argon diluent, can we somehow back out an air equivalent value for these experimental measurements? And so in order to look into that, you really have to understand, I think, the difference between a flame speed measured in, say, a diluent with argon and a flame speed measured in air. And so there's 3 main candidates here, right? So differences in flame speed are typically driven by transport properties, thermodynamic properties, and chemical kinetics. And so we went through a little bit of a thought exercise here. What I'm showing on the left, these are laminar flame speed predictions. This is just stoichiometric propane at 1 atmosphere and at various temperatures. But we see this black line here. These are the flame speeds predicted in argon or in a diluent that has argon in it. Sorry, in a fuel mixture, fuel and oxidizer mixture that has argon in it. And then in the bottom here, this is now the flame speed in air. So you do see a difference, right? We do see a faster flame speed in argon. That's to be expected. So we decided to do a bit of a thought exercise in order to figure out, okay, which of these factors is actually dominating and controlling this difference in flame speed. And so what we first did was, bear with me here, we took the transport properties associated with argon and swapped them for the transport properties of nitrogen, right? So all we're changing here are the transport properties in order to understand how do the transport properties specifically impact the flame speed. And so here, if we modify, again, the argon transport properties to be that of nitrogen, we get the following result. It's really not that different, actually. And so what that tells us is that the transport properties of these diluents that we're using, argon versus nitrogen, it's really not transport that's leading to this flame speed difference. So now we did this thought exercise again, but instead of modifying the transport properties, we modified thermodynamic properties, and here's what we get. So we actually see that the thermodynamic properties make a huge difference, right? We see that basically this is the dominant factor that leads to a flame speed measured in argon to be much higher than a flame speed measured in air. And so this really boils down to the difference in specific heats between the 2 diluents, right? Specific heat of argon is less than the specific heat of nitrogen. So what that means is that it takes less energy to heat up argon, say a degree, right? Which means that we end up with a higher adiabatic flame temperature and therefore also a higher flame speed. So knowing this, knowing that the difference is predominantly due to difference in thermodynamic properties, we set about trying to figure out, could we therefore scale our measurements? So for example, if we have measured a flame speed in argon, so here, for example, can we determine a scalar that would allow us to go from a measurement in argon to a measurement in air? So all the scalar is really is just a ratio of, say, laminar flame speed measured in air, so something along this green line, for example, over a flame speed measured in argon, so something along this black line, for example. So can we define that ratio as a function of temperature and then use that to scale our argon measurements into what we would call air equivalent measurements? So we wanted to verify that this approach works. And so what I'm showing here, the gray points here are 4 different measurements using the shock tube flame method in argon. And now the bottom line here shows, this is the kinetic model simulation, but the data points, these are all literature results And then the green points here are our shock tube measurements of the flame speed now in air, right? So the bottom segment here is all measurements in air, whereas the top here is in argon. So if we define a scalar, as I mentioned on the previous slide, what we can do is then scale these gray points down to be air equivalent points, right? And so what we find, in order to sort of verify that this method works, we find that these scale values actually agree within 1% of our pure measurements. So our measurements of flame speed in air agree within 1% of those argon-based flame speeds being scaled to air. So we see close agreement with measurements acquired in air and with literature results that were also acquired in air. So this allows us, therefore, to take our argon measurements, which we report in the literature, but also try to make them a little bit more relevant and useful for people who are, for example, doing CFD modeling. So next, let's take a look at some air equivalent flame speed results. And so we see those here. So the colored symbols are literature results, and then the gray symbols are our air equivalent flame speed results measured in the shock tube. We have some points here that were actually measured in air, so we saw those on the previous slide as well. So one of the main things that we see here, and then something that's very encouraging, is that our measurements in the shock tube agree closely with literature results at overlapping unburned gas temperatures, right? So we do see that these points overlap with what is existing in the literature, and that's encouraging. Now, before the advent of the shock tube measurement method, a lot of times that the way that we would obtain or estimate flame speeds at these high temperatures was to use empirical fits. So for example, power law fits. And so what we wanted to look into is, now that we have this data at high temperatures, do those fits still hold, and do they perform well and match these experimental measurements? And so what we found, these lines here, the dashes are now extrapolating these fits out to high temperatures. What we find is that systematically, these power law fits actually underestimate these high temperature flame speeds. Something we wanted to then look into, okay, is there a better functional form that might match or better fit this data? And so what we propose is the use of what we're calling a non-Arrhenius fit. So you'll notice it looks very similar to the power law fit, but now we've added an exponential term here. What we see is that this fit actually does capture both the low temperature data and the high temperature data in a much better way than, say, these power law fits. And so this is, if we now also apply this to some of the other fuel mixtures that we were looking at. So now this is again E50 here, and now we're looking at E85. We see similar trends, right? We see the power law fit, well, I'm not showing it here, but the non-Arrhenius fit does a good job of capturing the high temperature flame speeds as well as low temperature flame speeds. And that is something that we think is really a big takeaway here, right? Power law fits are not very good at capturing high temperature flame speeds. Something like a non-Arrhenius fit is actually a much better functional form. All right, as we approach the end here, I wanted to give you a little bit of a sneak preview of some of our ammonia flame speed work. Ammonia is a big topic in the community right now, and so we are also looking into this. So I thought folks might want to take a look at some of our most recent work. So again, we're using this shock tube method in order to measure laminar flame speeds of ammonia at a range of temperatures. So we're looking at 477 to 770 Kelvin, shock heated to 1 atmosphere at a range of equivalence ratios. So what I'll show here at the bottom left, this is now a video of one of our ammonia experiments. So this one's at post-shock heated temperature of 704 Kelvin. And again, this is ammonia in argon. Incident shock, reflected shock, and then we see spark ignition and the propagation of this ammonia flame. Very slow. And over on the right, I'm showing you just some additional experiments at additional temperatures. And you see ammonia flames are difficult. They're difficult to work with. But nevertheless, we are still able to extract flame speeds from these sequences of images. And here's a look at some of our preliminary argon results. So these are ammonia flame speeds measured in argon. The data, experimental data, is in the blue squares. And then we're also showing some kinetic modeling results from various kinetic models. So one of the first things that jumps out at you here is that there's wide disagreement in the predictions that we see from the various kinetic models. That's to be expected. I think everything is a work in progress right now. However, we do see, at least from the stoichiometric case here, that it does seem that the Okafor model from 2019 does seem to capture our experimental results the best of the 5 models that were considered. And now if we then report these as air equivalent flame speeds, I'm showing here the blue points are still the measurements in Aragon. The green points are now the measurements that have been in Aragon that have now been scaled to air. And so again, we're always doing this check. Do these air equivalent measurements match with available literature data? And so we're encouraged to again see that yes, they do at the lower temperatures. All right, and so yeah, I would say stay tuned. We're currently preparing this paper and hope to submit it for publication shortly in order to get some of this data out there. So that brings me to the end of my talk. If you take anything from this talk, I would say let it be that the shock tube laminar flame method allows us to study laminar flames at previously unexplored high unburned gas temperatures. I walked us through sort of the development of this approach over the years and how we have now adopted what we call the 2nd generation laminar flame method, which includes now the use of argon as a primary diluent instead of nitrogen or air. We're now also using a new optically accessible test section that allows us to do simultaneous sidewall and end wall imaging. And we've now adopted an area average linear curvature model in order to interpret our data. I then showed 2 case studies, but the ethanol flame speed case study in particular showed that kinetic models can accurately capture these high temperature ethanol flame speeds as long as they're actually using appropriate small molecule reaction rates. And so we showed that, for example, for some of the 3 top small molecule reactions, that just by bringing those into convergence with available experimental results, we see large improvement in the kinetic model predictions. We also noted that the power law fits that have conventionally been used to extrapolate low temperature flame speeds up to high temperatures, they don't accurately capture the high temperature trends that we're actually seeing in our data. And we propose using something like a non-Arrhenius form in order to capture those high temperature trends. And then finally, I provided basically a first look at some of our most recent ammonia flame speed work. Looking ahead, I'm really excited about this method. I think there's a lot of research and good science to be done here. Obviously, we want to expand the number and the types of fuels that we're studying with this approach. So looking at biofuels, fuel blends, real fuels, and also pushing to additional pressures, right? So all the data that I showed today was acquired at 1 atmosphere. And so we're looking to try to push up to higher pressures if possible. And outside the realm of just measuring laminar flame speeds, I think there's a lot of interesting novel flame phenomena that we can look at with this approach as well. So for example, looking at the impact of pre-ignition chemistry on laminar flame propagation, or looking at flame shock interactions, flame wall interactions, hemispherical flames. I think the list goes on. And I'm happy to talk offline with anyone who's also interested in trying to use this approach to study new phenomena. So with that, I'd like to thank, first and foremost, the Stanford Imaging Shock Tube team. So that's Dr. Adam Sousa, Jackie Zhang, Dr. Miguel Figueroa Labastida, and Zach Nygaard, and also the support of our principal investigator, Professor Ron Hansen. And then I'd like to thank the National Science Foundation and Total Energies for ongoing support, and also the NSF and the U.S. Army Research Office for past support for this work. And with that, I'd be happy to take any questions. And I've also given you 2 ways to contact me if you have questions offline. So thank you for your time. I appreciate it.